In this video, we're going to be talking about sets of numbers. Sometimes we look at sets of numbers and we kind of wonder, like a lot of things in math, why we need to know this. And we think that maybe it's something more out of a different class. It's a purely definition-based sort of thing. And why do we need to know the names of these different sets of numbers? But it is important because we're going to be talking about these things. You talk about it throughout algebra, and if we're referencing something, we need to have a certain word for that, a name for a type of number, so that everyone knows exactly what we're talking about. It's kind of like a situation we could relate it to our country, or any country for that matter. That you could break people down into different groups for where they live. You could have everyone in the whole country. You could say that's a set, the set of people that live in America. You could all have a set of people who live in a certain state, Arizona, California. You could then break that down by the city or the part of the city, the neighborhood. And each one of these separate sets is a smaller, more specific set of people. We can do the same thing with numbers. And just like it's important to maybe know where somebody lives, and you want to say they live in a zip code or this city, we want to know a certain number we're talking about. And just like we would talk in big groups with people, we can talk, and we need to start out in general sense with numbers. And the two biggest groups we can break these down into, the two sets, would be real numbers and also imaginary numbers. All right. Now, the thing is with imaginary numbers is we won't be talking about them too much just yet. I kind of want to explain the basics of imaginary numbers, but it will be something that will be covered more in depth later on, in later chapters. For right now, the difference there between real numbers and imaginary is when we think of real numbers, we think of things that are very tangible. They're real to us. I think these are great names for them. You could ask for a real number, that number of slices of pizza, and you could get it. You could take that many steps. You could walk around your neighborhood and go that many miles or kilometers. Whereas imaginary numbers, we can't actually really fathom it. It's not something we can put in our hand or take that number of steps or have that many slices of pizza. It's truly an imaginary number. And the way to quickly explain that is think of a square root. If you have a square root, say the square root of negative 16, okay? The definition of a square root is that it has to be a number times itself that equals that. So to find the square root of negative 16, we would need to find a number times itself that equals negative 16. Sometimes suggestions that are thrown out would be the number negative 4. So if we took negative 4 times negative 4, what actually happens is we get a positive, because a negative number times a negative number is a positive number. That would equal 16. Well, we might say, well, what about 4 and 4? We also, if we take a positive number times a positive number, get a positive. The only way we can get negative 16 is if we take a negative number times a positive number. That will give us negative 16, but it's not a square root because those are two different numbers. Negative 4 is different than 4. Thus, there's no real way to get the square root of negative 16. So we would say that the square root of negative 16 is an imaginary number, and we will learn about this later on. But for now, we're going to kind of break that apart. We'll be talking about, put that aside on the other side of the ledger there, and we'll be dealing with real numbers in this chapter. And we can break real numbers down into more and more specific sets, just like I talked about with people that live in a country or a state or such. Real numbers in general, these are numbers, like I said, that you can actually, they're tangible. They're things we deal with on a daily basis. And it would be all those numbers, all encompassing. Now, if we broke this down into two different sets to kind of split real numbers apart, so we're going to kind of split that off, we would split it up into rational numbers and irrational numbers. Okay? Don't really have enough room to spell it all the way out there, but I will in a second. So we have rational and irrational. So let's kind of clear this here. And if we have rational numbers on this side, and then over on this side, let's say we have irrational numbers. Okay? Now with rational numbers, there are certain things that define a number as being rational. And one of them is that if it is a certain number, it terminates. The other thing is it could repeat. You might say, okay, that seems like math lingo. What does that actually mean? Well, for a number to terminate, it would be something like, say, 3.23. It stops. It doesn't keep going. The decimal place stops there at 0.23. It doesn't continue on. And that would be something that terminates. You think of the word, if the word terminate means to stop, essentially. You also could have something like just the number 5. Or the number 200. These are numbers that terminate because there aren't decimal places that go on forever and ever and ever. So that's the terminate side of rational numbers. The other side of that is if something repeats. So a number that repeats would be, say, 3.3333. That's repeating. So 3 goes on forever. It repeats to infinity there in the decimal place. And that's when we kind of look at it. It seems, okay, that makes sense. It repeats 33333, it continues on. But one that can be easy to skip over is if we had something like this. 3.545454. Initially, this may not look like it repeats. It looks like there's different numbers here, but there is actually a pattern to it, and there is something that's repeating, and that's the 54. It is continuing on forever. 54, 54, 54, 54. This would also be a rational number. Okay, we're going to learn something more in a second about how we can create rational numbers, but we'll need to talk about another set of numbers first, so I will get back to that. Now with irrational, these are going to be numbers that basically are everything that's not rational. The numbers where it does not terminate or it does not repeat. So numbers that go on forever and ever, something like 3.1415926, so on and so forth, continuing on and on and on with no pattern to it. Okay, it was not repeating, it's not stopping anywhere, it just continues on, and that is an irrational number. If you remember back to pi, pi is an irrational number. Also, a lot of square roots are how we get irrational numbers. Okay, so pi is an irrational number. A lot of square roots are, like say the square root of 3, square root of 5. You'll get a number that just kind of continues on and on and on without repeating or without terminating. Okay, now within rational numbers, okay, let's say if we clear this here. So we're not going to go anything more specific within irrational numbers, but within rational we can find some more specific sets of numbers. And one of those are integers. Okay. This is a really important word, I think, in math because there's a lot of times we will reference integers. These are the numbers a lot of us think of as whole numbers. They're the numbers without decimal places on them, but it includes all the negatives and the positives and 0. So numbers like -3, -2, 1, 0, -1 there, 0, 1, 2, 3, 4, etc., etc. It is all those numbers without decimal places on them. The decimal is a 2.0, 1.0. There are no numbers there in the decimal, and they include 0, includes negatives and positives. Those would be our integers. Okay. One kind of interesting thing about integers is we can use this to relate back to rational numbers. If you take any two integers and you divide them, okay, if we took the number 1 and the number 3 and we divided that out, we would get 0.333, so on and so forth, continuing on, repeating. That right there is a rational number. And so even though sometimes it seems like you get some odd, weird numbers when you divide two integers, you will always get a rational number. So it's something to remember that you can always create a rational number by dividing two integers. If you don't believe me, try it out. I guarantee you either get a number that terminates or it is a number that will continue on forever. Another even more specific type here, a more specific set, are the natural numbers. Okay, these we don't reference as much as we do the integers, but with the natural numbers, these are kind of just a specific set of integers, and these are what we a lot of times refer to as our counting numbers. Okay, not the negatives, not 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., etc. Those positive numbers without 0 would be referred to as the natural numbers. Okay, so that's just one more set there. So we start out big picture. We have real numbers, we have imaginary numbers on either side, and then as we go through the real numbers, we can get more and more specific, and we can talk about rational and irrational. And then inside the rational numbers, we have integers and natural numbers. All right, so those are the different sets of numbers. Initially, it can seem like a bunch of definitions, but look them over, and it is nice to understand them because then as we progress through algebra and we're talking about certain numbers in relation to a concept, we'll know exactly what we're talking about. All right, thank you.